Hello, everybody. Apologies for the delay in starting tonight. Zoom has been giving us a little bit of grief, and the link that was in the original calendar invite turned out to be incorrect for some reason. Don't know why, but hold my hands up because I'm the one who sent that out. But hopefully people can join now because we've sent a new link round. For those of you who are new to this meetup, yeah, we are AnyTech, probably one of the largest tech meetups, I would say, in the Northeast. We're a tech agnostic group. So what I mean by that is our talks can be about any tech. Hey. But equally, we like to create a safe space for everybody, which is kind of free from recruitment. Usually we do these sorts of things in the gate, in the control pad, for those of you kind of who've been there before. Good little place. There's loads of little games and things and consoles for every other thing and PCs and it's interesting place. Usually we have beer and pizza as well, but unfortunately we've moved to a virtual meetup because of obviously COVID. But that doesn't stop us from bringing you fantastic talks. I'm dead excited for tonight because it's set to be a class talk. But who are we? So we've got myself. Hi, I'm Chris. And then we have James, Mark, and Martha, who also help to organize AnyTech. You want to give us a wave, James? I know Martha's got her camera off, but but yeah, if you want to get in touch with us, there's our kind of social media handles. Any questions about AnyTech or any questions for Cameron, we can obviously forward those on. We're also all over the kind of general social media, Facebook, Twitter, LinkedIn, Meetup, even on Discord as well. I don't expect you to remember that link though, unless you're a genius. So it's easier just to go to the website, any.technology, and there's a link at the top of the page where you can join that Discord channel. Big thanks to our sponsor, Scott Logic. Without those guys, we wouldn't really have a meetup. It's big thanks. Couldn't have done it without those. So our speaker for this evening, we have Cameron Trotler, who is a PhD student from Newcastle University. And he's going to be talking to us about his research into using machine learning and applying it to marine life on planet Earth. So without further ado, I will pass it over to him. If you have any questions, please do just pop them in the chat and we can address those at the end. So yeah, Cameron, if you want to share your screen, it's all yours.
Okay, so let me just sort my screens out. There we go. Hello, my name is Cameron Trotter, and I'm a PhD student in the School of Engineering and the Cloud Computing for Big Data CDT at Newcastle University, and I'm going to give a brief kind of introduction to kind of the work that we do at Newcastle, and then kind of look at my own research. So what are we going to cover today? So like I said, I'm going to kind of give a brief introduction to conservation tech at Newcastle, and then we'll take a look at my own work in automatic photo ID. So we're going to look at what photo ID actually is and how you automate it. And then kind of a brief note on like if you are really interested at the end of this talk in using the expertise that you have to aid conservation, how you can get involved with those sorts of endeavors. So a bit about me. I'm a third year PhD student. I'm based in the School of Engineering on a technicality. I would consider myself being based in the School of Computing. My background is in computing. I did my MComp at Newcastle University from 2013 to 2017. And prior to my PhD, I had absolutely no machine learning or deep learning experience at all. And my work itself focuses in this area of conservation tech, which is kind of a new emerging niche area, trying to employ technology to aid in conservation efforts, both fauna and flora. And I'm also currently on the hunt for internships. So a bit of nomenclature before we start. I'm probably going to say the word cetacean a lot during this presentation. And if you are like me when I first started my PhD and you have absolutely no idea what the word cetacean means, just think dolphins, whales, and porpoises. I'm probably going to use the word dolphin and cetacean interchangeably here. That's because the subjects that we work with are primarily dolphins, but the work applies to all cetaceans. So a bit about conservation tech at Newcastle. We're kind of a new group, I suppose. We're not a fully fledged lab or anything. It's just, a group of us. And our work focuses in machine learning aided marine conservation specifically. We focus on marine conservation, one, because Newcastle is a coastal city. And that means that the work done by conservationists in Newcastle is primarily marine based. So we work pretty closely with the School of Natural and Environmental Sciences Marine Megafauna Lab to do that. My work itself focuses on automated photo identification, but we also work with bioacoustics monitoring and reinforcement learning to train drones, underwater drones, to track the animals themselves. Yeah. So why do we focus on cetaceans? The monitoring of marine ecosystems has become increasingly important over the years. Things like climate change and pollution of the waterways is more known, and it's in the public domain more now. And one way that we can monitor the waterways is through monitoring the inhabitants of the water. And the reason that cetaceans are used is because they're top predators, they're top of the food chain. So if they're fit and healthy, it's usually a good indication that everything under the water and under them in the food chain is also healthy as well. So one of the ways that marine biologists and conservationists monitor these animals is through a process known as photo identification. So this is where the conservationists literally go out on a boat into a survey area. So our survey area runs from kind of around Sunderland all the way up to the top of Northumberland. So they go out and they survey the area, drive around in the boat, and collect photographic data of any encounters. So anytime they see a cetacean come up out of the water, they would take a photograph of it, and then these photographs are taken back to the lab to perform individual identifications. So they identify the individuals based on some prominent markings, primarily on the fins that come out of the water when the animal breaches. And knowing the individuals in your survey area is really important for things such as population dynamics and ecology, so health assessments, things like that. And yeah, so we focus on it because it is one of the favored methods of the Marine Megafauna Lab, who we work quite closely with. So what sorts of things are they looking for? So there's kind of four main types of prominent marking. So one of the most common is nicks. So you can see there kind of on the trailing edge of the fin, there's a lot of kind of sections that are missing. So we use those to identify the individual. They can be from kind of social interactions with other animals or through human interaction. We're also looking at scarring. This is a particularly bad example, or a good example, I suppose, if you're not the dolphin. And so this would have been caused probably by a boat strike or a propeller or something like that. We're looking for any scratching. So this scratching is usually kind of long term, so something that isn't going to fade while we're working in the survey area. And we're also looking for pigmentation. So this sort of stuff can be either naturally occurring or can be the result of things like pollution in the waterways or disease. The Marine Megafauna Lab are quite unique in that they also deal with underwater photo ID. So in this case, we're looking for any identifying information at all on the animals. So primarily the head, the ventral, which is the underside of the animal, the dorsal fin, or the tail stalk. So I wouldn't be doing a PhD in automating this process if there wasn't problems with manual identification. And the two kind of main ones is that one, it's really, really time consuming to actually perform. So as an example, the fieldwork that was undertaken in summer 2019 off the Northumberland coast, bearing in mind that these fieldwork seasons themselves are about 6 months, it took another 3 months to go from the raw images captured during the fieldwork to having something that resembled an identification catalog that could be used. And it's also really prone to error. So IDing the individual in the photograph relies on the individual being recognized by the person who's performing the identification. So there's a big risk of mislabeling here. The animal can either be identified as another individual in the catalog or given an entirely new ID so that there's now one individual with two IDs in the catalog. So my research kind of tries to answer this question of, can we utilize machine learning to build a fully automated photo identification pipeline to help speed up this process so that conservationists can actually spend time like thinking about conservation and not about how they need to prepare their data. So this is kind of a general overview of my research itself. So the whole idea is, can we take these input images, so the images directly from the camera, so taken off the SD card on the camera, loaded into the computer, and then running this program. So we're trying to, one, perform detection to see if there are actually any fins in the images. Then can we segment that fin out? And then can we automatically identify the individual in the image? And like I said, this is all done through machine learning. And the use of machine learning for solving kind of image-based tasks is a pretty well-founded area of research. Kind of in production systems or in business, anything like that, a large proportion of image processing is now performed utilizing some form of machine learning. And of that, pretty much all of them will be using what's known as a convolutional neural network as a backbone. So I don't know how much kind of machine learning knowledge people have here. So I'm kind of going to give a very, very quick primer on convolutional neural networks. Like, it's not going to be anything technical or really, you know, groundbreaking, but it keeps everybody at the same page for when I'm talking later. So in 3.5 bullet points, what is a convolutional neural network? In essence, a CNN is an algorithm which takes some input image and it can learn to assign the importance, some importance to parts of the image in order to achieve some goal. And the really cool thing about CNNs is that this kind of importance of features is learned through some training process, which makes CNNs extremely generalizable. So now there isn't this need to kind of hand engineer specific methodologies based on the data that you have and the task that you want to perform. You can create a CNN to be able to do it. And these CNNs operate by connecting various layers together, which each performs some standardized set of operations. Again, I'm kind of not really going to go into them, but if we look at the image on screen, so we take an input image and we run that through various layers. So you've got a convolutional layer, a max pooling layer, fully connected layers. and then you have some output. So those output nodes, they are nodes labeled between 0 and 9, and the whole point of this CNN is to be able to recognize what digit is in the input image. So now that we kind of understand that, and we understand the goal that we want to achieve, we can start to split this problem up into smaller subtasks. So the first step, like I said, was detection. So we're wanting to find any fins in the input image. Because these images are coming directly from the SD card, there is the possibility that an image contains no fins. Because the image has been captured by accident. For example, it's just the bottom, the floor of the boat. We then, if there are any fins in there, we can try and segment those from the image and clean them up and do some processing on them. And then we can perform this individual identification, this classification, to determine which individual the fin belongs to. And we can break this kind of problem specification down a little bit further with this idea that we have in machine learning and specifically computer vision of coarse versus fine-grained problems. So in a coarse-grained problem, you're kind of giving your classes kind of very broad labels. So all of those images there would get the label dog. Whereas in a fine-grained task, we're kind of going a bit deeper into our labeling hierarchy. So we would say, for example, that rather than dog, 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 where they all have the same label, they now have different labels, and it's poodle, Labrador, Shiba Inu. So applying that to the work that we do, the detection task is primarily a coarse-grained problem because we're only detecting based on dolphin, right? We don't care at this point who the individual is when we're trying to detect a fin. We just need to know, is there a fin there? The classification task, on the other hand, so the identification is a fine-grained problem, but we're going deeper than just say species labels, right? We're doing what's known as an extreme fine-grained problem. So in that image, at a coarse-grained level, we would say that there's dog, dog, dog. At a fine-grained level, we would say that there's poodle, poodle, poodle. But in an extreme fine-grained problem, we're assigning individual labels to the animals themselves. So, for example, one of those dogs is Vera, one of them is Luna, and one of them is Delta. And if I said to you, if I gave you that image and gave you those labels and said, I want you to label, tell me which dogs are which, you probably wouldn't be able to do that, right? Unless you were the owner of the dog or knew them really well. And that's kind of the problem that we face here, is that the system that we design needs to be capable of having some kind of expert knowledge on who these individuals are. So having CNNs do this is a pretty open research problem at the moment, like this kind of extreme fine-grained recognition. Because most current research in this domain focuses on interspecies differences like dog breeds or kind of makes of car, things like that. And any kind of extreme fine-grained research, chances are you're working with kind of facial recognition systems or person re-identification systems. And these conditions are really, really sterile, right? It's why passport photos have such stringent rules. So, take your glasses off, don't smile, look straight ahead, have a white background. It's to give the system as good a chance as possible as performing re-identification. On contrast, our conditions aren't sterile. We work in the North Sea. It's grey, it's rainy, it's windy, it's horrible. So that just adds another layer of complication to everything. So let's kind of take a bit of a deep dive, pardon the pun, into each kind of stage of the pipeline itself to kind of understand what's going on here. So let's start with the detector. So I'm going to throw around a lot of buzzwords here, and I'm sorry. But coarse-grained detection is performed using what's known as a mask RCNN. and the system that we use has a ResNet 50 architecture behind it. So there's this CNN called type of architecture called ResNet, and we use a ResNet architecture that is 50 layers deep. This network is pre-trained on Microsoft's Common Objects in Context dataset. So the reason that we train the model to first on this larger dataset is because the dolphin images that we have from fieldwork, there's not a lot of them. So neural networks typically need thousands or hundred thousands of images to train to a decent level of accuracy. So what we do is we take this larger data set from Microsoft, we train our mascar CNN to be capable of detecting and performing well on that data set. And then we essentially chop off kind of the layers at the end of the network and then bootstrap in this dolphin detection task. And the reason that we use a mascar CNN over other CNN implementations is because this allows us to have not just bounding boxes, which you would usually get with an object detection task, but also pixel-wise mappings for the objects. So rather than being able to say, yes, there is a fin in this image and it is somewhere kind of in this general area of the image, we can say, yes, there is a fin in this image, and these are the exact pixels in the image that the fin belongs to. And this makes it far more simpler to perform kind of the segmentation downstream. So one of the downsides of this is that the mascar CNN system is kind of really, really bulky. And training is very, very expensive, both computationally. So we run this, we train these models using Microsoft's Azure platform with 2 dedicated GPUs, 2 Tesla K80s. And it takes a good few hours to train with that. But also kind of from an economic perspective, in that labeling this data is really quite labor intensive and expensive to do. Because you have to label each individual pixel in your training data rather than just kind of drawing a box. But yeah, so kind of mascar CNN was released in 2018. So kind of any improvements here, there's still a lot of room for improvement in how bulky and how long the system takes to train. So any kind of improvements here would help the entire pipeline. So now let's take a look at the segmentations. So now we've run our input images through the detector, and we filtered out any images that don't have fins in, and of the images that do have fins in, we know kind of where they are on a pixel level. So we perform segmentation on those fins, and what we do here is we essentially remove kind of all of the background noise. And this kind of improves the chances of identification because dolphins are, and cetaceans are, they're grey, and the North Sea tends to be grey, so they're very well camouflaged. But that means that our system sometimes really struggles if there's any background in there. And by performing segmentation as well, it reduces the computational expense of future operations. So another reason kind of why the mascar CNN detector is really bulky is because of the fact that it's working on images that are 5,000 by 3,000 pixels wide, right? They come kind of directly from a DSLR camera. What this the segmenter allows us to do is reduce that image size down as much as possible, so that the identification system can be as lightweight as possible. And you'll kind of notice that that makes the data really, really clean by performing this segmentation. It's kind of like a passport photo, right? And this segmentation is kind of one of the stages that doesn't kind of use any like machine learning at all. This is just performed using the OpenCV framework. We use Python, the Python implementation of this, and it's essentially just kind of matrix computations to remove anything that isn't detected. So now we kind of get to the hard part of doing the individual identifications. So In order to implement a system that is capable of automatic photo identification, we're going to need a system that's capable of a few things. So number one, it needs to be able to accurately locate these identifying information in the segmentation. So that means it needs to be able to take that new image from the segmenter and identify the prominent markings, similar to how a human would in manual identification. We then need to compare the prominent markings that have been found to the information that is stored by the system. And there could potentially be very few examples of individuals in the system, right? So when the system is trained, it's trained using a data set from of individuals that we've seen in previous surveys. But there's no guarantee that every individual that will ever be seen is in that training data, right? Because the fact that they're wild animals, right? They're free roaming. We can't guarantee that we will see every individual that is in that survey area on every single fieldwork trip that is performed. So the system needs to be capable of handling that. And it also needs to be invariant to things such as rotation or like angle of approach that the cetacean is taking towards the bow when the photograph is taken. Occlusion, so the animals kind of they collect in pods. They're social animals. So usually, you know, if there is a fin in the image, chances are there's multiple fins and they're all kind of overlapping with each other. And the system also needs to be capable of handling fins that don't have any prominent markings on them at all. So, for example, calves, right? When calves are born, the chances are is that they don't really have any prominent markings on the fins yet. And whilst the conservationists themselves, they will just discard those images, right? They won't even look at that fin because there's nothing that they can identify on. Our system needs to be able to do the same, right? It needs to be able to get this fin, go, there's no prominent markings, and just discard it or flag it to the researcher, rather than, you know, being like, oh my god, I don't know what to do because there's no identifiable information here. So this kind of leads to a deeper problem of not just fine grain recognition, but it's what's known as a few shot problem as well, right? Because we only have very, very few examples of each individual. Potentially we have no examples of an individual, and we still need to be able to identify it as an individual. So one of the kind of new and up and coming ways of doing this, I suppose, is what's known as the Siamese Neural Network. So we utilize this for the automated photo ID. So I'm going to talk a bit about those now. So what is a Siamese neural network? Again, in 3 bullet points. So a Siamese neural network is essentially just a neural network that contains at least 2 parallel CNNs, right? So the work that we perform, our Siamese neural network has 3 branches, and that's because we work with what's known as triplets. So I'll kind of delve into that in a second. But yeah, basically what you need to know is that there's at least 2 parallel CNNs and that these CNNs are completely identical. So when I say identical, they have exactly the same architecture. They share the same weights. So what weights are is these are the parameters that are learned during the training process. So basically when one CNN learns something and updates itself to work with this new information, all of the other branches update in exactly the same way. And they also share the same hyperparameters. So hyperparameters are just values that you set before the training process begins. So these are things that the model can't learn, but needs to have a value set in order to operate. And the really cool thing about this is that when you branch CNNs in this way and parallelize them, what you can then do is you can take images and reduce them down to a really, really kind of low level representation, what we're going to call an embedding. So there's this idea of a d-dimensional embedding, where d is just some number that you decide on, right? So let's say you have a 10-dimensional embedding. What the network is capable of doing is taking this input image and reducing that down to essentially just a 10 numbered representation, right? And what you can then do is take that representation and plot it into some hyperspace. So imagine just as a graph, right? You're essentially just plotting it along an XY axis, just with a lot more axes. And then what we can do is compare those embeddings to produce some similarity metric, right? So if we take the example on screen, so we're feeding in 3 images. Image 1 is called the anchor, and that is an image of the class that we want to train on, right? So we have an image of class 1, and we want to train our Siamese neural network to be capable of embedding ones, right? So we provided a positive as well, which is another example of the class. And then we provided a negative, which is another image, which is of a different class. And so each CNN produces an embedding for those images. And then we can plot that into the hyperspace. And the whole idea here is that the Siamese neural network learns how to manipulate those embeddings in such a way that those images of ones will be really, really close together when it's plotted, but the images of the ones and twos will be really, really far apart. So what this allows you to do is essentially generate clusters of classes within the space, right? So all of your images of ones are really, really close together, but all of your images of, the difference between ones and twos, those clusters are really far apart. And this is kind of the important distinction. If you don't take anything else away from this talk, this is the slide. It's that if you have a CNN on its own, it can predict a classification. It can tell you that there's a 2 in an image. But once you branch them together and have this notion of being able to plot the output of those CNNs, you can then start to develop some idea of similarity. So you can say how similar 2 images are based on this clustering. So that's kind of why we use them. Because of the fact that they can produce a similarity, they're extremely useful for when we're working with open data sets. And by open data sets, I mean data where the set of classes is constantly changing, which is really, really common in conservation. So for example, the individual characteristics can change over time. New individuals could be born, they could migrate into the survey area, individuals will die as well. And this allows us to be capable of handling classes that the model has never seen before, right? The whole idea is that if you have an individual that has just entered the survey area and it was never in your training data, that's fine. The model can handle that because the network should embed that individual into the space in an entirely new location compared to all of the other individuals that it's seen before. So we can then flag that to the researchers and the conservationists and say, these are all of the individuals that we found, but there's this new kind of cluster that's been created that there's either a problem with the network or this is a new individual that we've never seen before in this survey area. So training Siamese neural networks is performed using what's known as a ranking loss. When this loss just allows you to update the embeddings and works between these distances metrics. And if anybody's worked with kind of natural language processing tasks like document ranking, we're basically kind of performing the same thing here, but with images in a way. The really, really cool thing about Siamese neural networks is the fact that at inference, so when we deploy these models, we don't actually need all of the branches of the CNNs. We only need one, because now that we've trained the model to produce these embeddings, we just need to start feeding images in, right? So we can just do one at a time, and this will produce an embedding and allow us to plot them. So this makes them quite computationally expensive when you're training them, but really lightweight when you're actually deploying the models. And yeah, so like I said, we now have a system that can take in a fin and give us some, based on distances with the clusters that it's seen previously, most likely identifications. And there's just so much more that I could talk about with Siamese neural networks. I just find them really, really interesting. So there's just so many different problems, like how many branches should you have? How many CNNs should you actually put in there? How does this affect training? How do you pass the data to the Siamese neural network? How do you even program one? So if anybody's really interested, I've wrote about all of this in lots and lots of detail. The QR code's there if anybody wants to read it. Because I think they're really interesting, but there's just so much to cover. I couldn't do it all in one talk and give you this idea of conservation tech. So hopefully you can kind of see how we can utilize machine learning to help in this space, and how we can push the boundaries of what is possible in machine learning, both from a computing perspective of being able to develop these kind of novel architectures, but also how we can then apply machine learning and technology to areas where it would never have been, never even been thought of being applied, because a lot of conservationists, they still work with methods that were developed in like the 70s and 80s because they work and they don't have the expertise to be able to advance, right? And introduce more technology-based approaches. So if you're kind of thinking that this idea of helping out with conservation sounds really, really interesting, there's a few places that I would point you to. Probably the most well-known is a system called Wild Labs. And Wild Labs is basically an online community that connects conservationists to programmers. And it doesn't need to be machine learning. It can, there's posts on there of, people who are working out in the field and they go, oh, we really need this embedded system, but we don't really know what we're doing, or we need a database. How do we set a database up, right, to track the animals that we're tracking? Like the conservationists, they have all of these ideas, but they don't know how to implement them. And then at the same time, this allows you to connect with programmers who want to use the expertise that they have for good, but don't know where to start, right? So if you're wanting to get involved, I would really highly recommend Wild Labs. We're also kind of running a competition, Kaggle competition for automatic photo ID, which will be coming later this month. And this is not just from my own data, although if you want to have a play around with my data, it's all open sourced. There's another QR code there. But this is kind of a joint project between marine conservation groups and cetacean research groups all over the world. So everybody's kind of pulled their data together to kind of help develop these systems. So I think if you were wanting to get involved in automatic photo ID, that would probably be one of the best ways to start. But yeah, thank you for listening. That's my talk. I hope you found it interesting, and yeah, I'll take any questions now, I suppose. Thanks.
Yeah, so one of the questions I had actually was one of the questions on one of your previous slides, which I guess maybe didn't have time to go into, but it was around kind of branches on your CNN. So do you eventually kind of hit a limit where kind of like when you overtrain a neural network, if you throw too much at it, then it kind of has a negative impact? Do you reach a point where if you have too many branches, then it starts to kind of deteriorate the performance?
Yeah, so generally what you'll see is networks that have, so when Siamese neural networks kind of started becoming a thing, there was always two branches. And then in about, I think it was about 2017, this idea of using three branches came around. And now we're kind of working towards, well, is four branches a good idea? And there's, some evidence to suggest that four branches is better than three, or that, three is better than four for certain tasks. But I suppose kind of a lot of it comes down to, it comes down to really the loss function, right? So how the model learns and how many inputs that needs is really kind of the deciding factor in your branches. But then there's also kind of, I suppose, a computational cost to that, because you need to have a system that can actually accommodate, you need to be able to have enough GPUs to be able to do this, right? And most people aren't Google and have like 10 million GPUs that they can just throw at a problem. So I'd say that that's more of a concern rather than the problem of overfitting the models. The overfitting of the models is really more of a concern with the amount of data that you have. So again, like I've said, our data set for doing this is relatively small. So we do things such as we augment the data. So what that means is that we create new data based on random perturbations of the data that we have. So kind of when we feed it into the model, we say, for example, we randomly, flip the data, or we change the contrast, we change the brightness, we add noise to it. And that's how you can kind of prevent those models from overfitting. It's also kind of one of the reasons why we use a triplet network is because you can perform a thing called triplet mining. So that's like kind of deciding how what triplets you will actually pass to the network, and if that coupled with your data augmentation is really kind of the deciding factor in how the model fits.
Right. Okay.
Does that answer your question?
Yeah, I think it does. I'm just I'm going like, right, okay, because it's just like a fascinating subject, which
Yeah,
I would love to know more about.
yeah, it's really fascinating, and it's really annoying because there is just so much to talk about. There's so many different avenues you could take a talk on Siamese neural networks down.
Do you have any recommendations for, like, if somebody wanted to go away and like start learning this sort of stuff? Are there any kind of sources that you would
Yeah,
point to?
I learned pretty much, if you're wanting a more academic route, you should be able to search for a paper called, well, there's a few papers. So kind of the first paper that introduced this idea of Siamese neural networks is a paper called SIGNET, SIGNET. And that kind of introduced this idea of Siamese neural networks for signature verification. So being able to tell if a signature is real or a forgery. There's also a paper called FaceNet, which introduced this idea of person re-identification through a triplet network. If you're wanting a less kind of, I suppose, kind of paper heavy and very, very academic route for learning this kind of thing, there's a really, really good course on Coursera, and I forget the name of the person who wrote it, but it's really, really good. If you search Coursera Siamese neural network, it's kind of a very kind of, I don't want to say hand-holding guide, but it really introduces kind of the basics of doing this kind of thing.
Cool. Okay, I'll definitely have to go and have a look. Cheers.
No problem.
Any more questions from anybody else? Feel free to chuck them in the chat or unmute yourself if you wanted to ask anything. Cool. All right then. Brilliant. Right. I guess that then. Thank you very much, Cameron, for that. Yeah, really, really interesting talk.
Thank you for having me.
Not a problem at all. I'm just going to take the screen back if that's all right.
Yeah, it's fine.
Cool. Okay. So yeah, if anybody had any questions which they thought of later, you can get in touch with Cameron either via us or you can get him on Twitter there at Cam Trots. Yeah, or any questions around any tech, just get in touch with any of us via any of those social media hooks. We always appreciate feedback because we want to make this a meetup for you guys. It's not really for us. Well, we like to see amazing talks, obviously, but you guys make any tech. So any feedback for either the AnyTech crew or for Cameron, that's much appreciated. Coming up next month, so we have Ali Spatel, who works at AWS Amplify, and she's got a talk which I think she's done at a few different conferences now. Definitely worth joining for that one. That's 8th of April. Hopefully I'll get the Zoom link right this time around. Once again, apologies for that. But just once again, I want to thank you, Cameron. Awesome talk. And I'll hopefully see everybody next month. Thank you very much for coming. Cheers all.